Okay, so let's talk about the electric field from a finite line charge. So you have a finite wire which has a uniform positive charge on it and a total charge of Q. And you want to know what the electric field is some distance d away. So let's put it right in the center because that's going to make our lives a little bit easier. And we know that distance is d. So let me write down the question. So the question is, what is the electric field from a uniformly charged wire at a distance d from the center of that wire? So we're looking at for point P here. So let's start with the basics of the basic electric field equation for a point charge. Because we have what a line charge is just a series of point charges in a row, right? So let's just think about that equation. So that equation is going to be E is equal to 1 over 4 pi epsilon naught times the charge over the distance squared. Straighten that guy out a little. There we go. So yeah, like what we're looking at is a series of point charges along this line. So I have some point charge here, and then some other point charge here, let's say. And all around this wire, there's a bunch of them put in there. So if I look at what is the electric field from this point, well, it's going to act along this line and point that way, right? And from this line, we're going to get a similar thing from this point, and it's going to get electric field going that way. So what we have is, just we can find the magnitude of each of them. But the other thing we'll have to consider is that the x components point in opposite directions, right? And the y components point together. So this would be EY, down here will be EX. Those EX components with this side and that side will cancel. And they're going to cancel exactly because it's symmetric. And so they're all just going to add up. And there's going to be each point will have its opposite. So their y components are going to add together, but their x components won't. Okay. So we should say, what if we said that the value of the charge the charge in this little small position area, this little small segment of my line, is dq, right? You see where we're going with this. I mean, we only use dq's, and then we're going to add up all the electric fields from these. So what if I said that dE was equal to 1 over 4 pi epsilon naught dq over r squared, right? So now we just integrate both sides, and we're going to solve for E, for electric field. So now the problem here, though, is normally when we do integrals, you do them over a spatial dimension. You don't usually integrate over charge or mass or anything more abstract like that. There are usually spatial dimensions. So let's see if we can put this thing into a spatial dimension. Well, I know that dq, so let's say dq is going to be however long this bit is, right? So let's say it has a width of dx. So let's say dq equals dx. But we want to have the charge per length there, right? So we care about that. So we'll say q over L. And let's just simplify q over L as the linear charge density. So we'll say lambda dx. We'll use that. Now, R in this case is going to be the hypotenuse of this triangle, right? So if I draw this triangle here, it's got this side will be x, this side will be, well, this side is y or d in this case, so I'll put d here. So I should know then that r squared is going to equal x squared plus d squared, right? Which also tells me that r is equal to the square root of x squared plus d squared, if we need to write that down. All right. So we're almost done with this, except we're missing something, right? Because we said we only actually wanted the y components of my electric field. So this is so what happened with what do we do to get rid of the x's? Well, let's first, you put a y here, so you solve the problem, right? But the other thing I want to know is how to get the y component. If we call that angle theta, I need to say the y component. Well, the y component is going to be the sine of theta, right? So let's throw in a sine theta. So what do I do with my sine theta? Because it's not, I'm integrating over x. Theta is going to change as I change x, but how do I put that together? Well, on this triangle, I can look at it and say theta, well, sine theta is going to be opposite over hypotenuse. So I can say that sine of theta is d over r. And I can substitute in for r. So that's going to be d over square root of x squared plus y squared. All right? So let's start making these substitutions. So I'm just going to integrate to get electric field in the y direction, which is my total electric field actually. It's 1 over 4 pi epsilon naught times the integral. We should put bounds of our integral too. We're integrating from minus L over 2 to L over 2. So I'm going to put my 0 point right here, right in the middle, to L over 2 of lambda dx over x squared plus d squared times d over the square root of x squared plus y squared. Like that. All right, so I'm going to need a little bit more room, so I'm going to slide the paper up. Excellent. So let's simplify this. I can pull out my lambda and I can combine the MID and combine the bottom into one term. So I'm going to say then that I have lambda d over 4 pi epsilon naught times the integral from minus L over 2 to L over 2 of dx over x squared plus d squared, but that is raised to the 3/2. So now it's just a simple matter of integrating that. Now if you want to do this analytically and solve this integral by hand, it's a little challenging. So I mean, it's probably better just to look it up or type it into Symbolab or put it in your calculator, because I think your calculator can handle this too. So I'm just going to write down the answer. If you want to talk to me about how to solve this integral, we can do it during office hours or during our scheduled class time. But for now, let's just write down the answer. So we get that the answer here is going to be 1 over 4 pi epsilon naught, well, it's times lambda d. Let's just lambda d, forget the 1. I'm just used to writing 1 over 4 pi epsilon naught times, this is going to be 1 over d squared times I think it's going to be x over x squared plus d squared, and we're evaluating that. Oh, I forgot my square root. Square rooted. We're evaluating that from minus L over 2 to L over 2. So, only 1 or 2 more lines. Let's come to the right side just to finish this off. So we'll just bring this up here and say electric field is equal to lambda. Well, I can cancel that d actually, right? So lambda d over 4 pi epsilon naught d squared. I'll pull that guy out, so cancel that with that. Times L over 2 square roots of L squared over 4 plus d squared. And that's going to be minus L over 2 square root of L squared over 4 plus d squared. Right? So this 2 minuses cancel and turn into a positive. So now these are the exact same term. Well, technically this is minus L squared, but we squared the L, right? So it doesn't actually matter. So then electric field then is equal to, yeah, those are going to go away. So lambda over 4 pi epsilon naught, let's put an L over here, times 1 over the square root, and these 2's cancel when we add them, right, of L squared over 4 plus d squared. And this is going to be in the y direction if we care about that. So the y hat, in case you guys don't remember, just means in the y direction. And that is my answer. All right. So I want to do one more thing with this just to make it, take it a little bit farther. So what if I took this answer, let's rewrite this one again. I'll pause it. So what if I take my answer that we had a second ago and we say it is the electric field is equal to lambda L over 4 pi epsilon naught times 1 over the square root of L squared over 4 plus d squared. So one thing we can do if we want to simplify this a little bit or make it a little bit prettier is I can say lambda L over 2 pi epsilon naught, and I take one of those 2's, because 4 is 2 times 2, and put it and distribute it through here. So I square it to put it inside, right? Because I want the square root of 4 to be 2. So I'm going to multiply this by 4 and this by 4. So that's actually going to get me 1 over the square root of L squared plus 4d squared, which a lot of people like that better. But it's about the same, really. So, but what I want to do is, what if I said, let's do this in the limit that L is infinity. So I want to say, what is the limit of E as L approaches infinity, right? What is that going to get us? Well, if L goes to infinity. Oh, I missed a term. Dadgummit, guys, I missed a term. You didn't tell me. So I forgot way back here this d squared. I can cancel, well, I canceled this one with that one, but I left out that d squared here. So that's going to be my answer that we want. So back to what we're doing now, though. I need to have that d here for this to actually work. I'm going to leave this in without editing it, guys, just because I want you to see that you're allowed to make mistakes. It's just important to know, or to figure out what that mistake was. So I'll tell you how I figured out my mistake in a second. So what now, in the limit that L goes to infinity, I'm still going to have this first term. Well, I guess I'm going to pull this L over here, right? Because I want this lambda over 2 pi epsilon naught d times L over L squared plus 4d squared. So in the limit that L goes to infinity, this d doesn't matter at all. So we're going to approximate this guy and just say, we're just going to, say this guy functionally 0. So what I want to do then, I'm going to say, take this first term, leave this the same, and then I'm going to get L over the square root of L squared, right? Which is just going to be lambda over 2 pi epsilon naught d times L over L, which those guys both cancel, and that goes to 1. So my electric field then should equal lambda over 2 pi epsilon naught d. Which, let me slide that up so you guys can see it a little better. There you go. So that's what we said the electric field should be if the wire is infinitely long. If L is infinite. But earlier in another video, we said, let's use Gauss's law for an infinite line charge. So in theory, if we did this right and Gauss's law works, then we should get the same answer here. So what answer did we get earlier when we did that? Well, we got that the electric field was equal to lambda over 2 pi epsilon naught times the radius of that cylinder we drew. So we got the exact same answer. And there's my cylinder. So this works. We have two different methods that have agreed. So I'm pretty happy with that. And I think you guys should be too. This is a solid method. I think, so in the case that you have an infinite wire, Gauss's law is easier. But the case that you have a finite wire, doing it the way we just did is a little bit more robust. But it's also more involved. Anyways, I hope you guys learned something or maybe remembered something because we've done this before. But I'll see you guys in the next video.